came to Iowa State, and he actually worked with late Dr. Reed Palmer, someone I really, really admire. I think that person was ahead of his times. And coming to Iowa State, I think he realized that, yeah, I can go back to Kansas. So he went back to Kansas, Kansas State, completed his bachelor's, and then he came here to Iowa to start a PhD program in 2016. John is a part of the National Research Traineeship, the Predictive Plant Economics program. I think you're one of the first.
First cohort.
You're the first cohort in it. And John also has had some invitations. The most, for presentation, most notable was the machine learning for cyber agriculture system. That was the inaugural international symposium on it. So John went to India and he learned how to cross the road.
Barely.
Which is you just get your hand out and you just go for it. So, but it's my pleasure to welcome John and looking forward to you.
Thank you, Danny. Alrighty. So for those of you who don't know me or maybe don't recognize me without the K-State hat on, I am in fact Johnathon Shook. And I am going to be presenting today a little bit of my work on combining genetic and weather parameters to be able to predict soybean yield. And technology on always helps. So just getting into a little bit of the overview and motivation for this. We all are very, very familiar with this equation. Your phenotype is going to be dependent on the genetics, the environment, the interaction between the genetics and the environment, and then there's going to be some residual, anything that's not able to be modeled within that equation directly. However, I think we can do a little bit better job when we break down this environmental component and add in specific factors for management, soil fertility or texture, and especially weather. Recent advances in weather technology has enabled us to buy a weather station for maybe $1,000, put it in the field, and get up to, every 3 seconds we can get updated weather parameters. Obviously, we don't want to be trying to model every 3 seconds worth of weather data throughout the growing season, but it gives us a place to start and a rich data set to be able to start this project. A quote that kind of got me thinking about this a little bit more was a quote by Dr. Elwyn Taylor at a conference in 2012 at Kansas State. He said, "The weather is going to do what the weather does, manage the risk." Obviously, he was presenting this to farmers and not breeders, but I think that we as breeders can also take some insight from this statement. So weather variability has been actually starting to increase. It's expected to be in a very variable state from 2012 to 2036, and I'll get a little bit more into that in the next slide as well. We've seen an increase in temperature in the United States. This map is showing the temperature from 1991 to 2012 in the United States and the change that's happened over that. All of these are in Fahrenheit, so don't look at the numbers if you're used to Celsius. But we can see that most of the northern US has seen more of an increase, and then there's a little pocket of actually cooling temperatures in the southern United States. But overall, we have a warming trend, and this warming trend has helped in the northern United States, but been detrimental in the southern parts of the US. Both the variability and the increase in temperature that we've seen put the crops that we're growing into new challenges and present new challenges for breeders to be able to adapt for more drought occurrences, more heavy rainfall, higher temperatures, lower temperature extremes. All of these are new challenges that we need to find new sources of variability for to be able to breed for in the future. And this is where I was talking that we'll see kind of the stability. We can look at these periods that are within the orange boxes, and there's actually about an 18-year cycle of stable environmental parameters, followed by 25 years of more variable weather and thus variable yield. In my career, I'm going to be starting out with very variable weather, and that's a little bit scary because you can see that we have consistent yield gains when it's stable and a little bit less so when it's not. So that'll make breeding more of a challenge. But the question is, how do we breed in these variable years? Since we're going to be stuck for the next 17 years in this variable period, how do we best manage that, and how do we be able to track performance from year to year without biasing it based off of random weather events. So the objectives for this project is to predict soybean yield primarily for a location based solely on the weather. This was the first step in our project, and it's only looking at that E component of the equation that we started with. However, we also want to be able to bring in the genetics part in the G by E component. So we want to be able to predict performance on, in this case, pedigree and weather. These predictions are going to be based on performance in other locations for either that line itself or for related lines, because we can kind of develop BLEPs or something like that. And we want to work towards genotype specific predictions, whether it be with markers or with pedigree. We want to be able to increase the specificity of these predictions, which is an ongoing piece of work for us. And as long-term outcomes, we want to identify redundant locations within the uniform soybean tests. These tests are going to be going on for a long time. They've been going on for quite a while. And we want to enable breeding for future scenarios, whether that be drought, heat, cold, what have you. So the uniform soybean tests have been going on since 1941, and we selected 2003 to 2015. You can kind of see the locations as they change throughout the years, but you have a core set of environments that are consistently tested year in and year out. These tests have been ongoing since 1941 and are a collaboration between United States and Canadian breeders, whether it be the USDA or at research institutions like this. So we started out preparing weather data. We used GPS coordinates based on each field site as it was named, or when we were able to get a hold of the people that put them on, sometimes they were able to provide actual field locations for increased clarity. And we downloaded gridded historical weather data starting from April 1st through October 31st for each year that that environment was tested. These hourly records that we got from this were then reduced to daily, weekly, monthly, etc., so that we could test how it was going to perform on different temporal scales. And we have mostly the variables that are tested include temperature, precipitation, the sunlight intensity, and then humidity. So the uniform soybean tests come to us in PDFs or in printed booklets that are about 300 pages each for the North and the South. So in total, we're going through about 7,800 pages worth of data and trying to put these into a format that we can actually analyze, because I don't know about you, but I don't have anything that can handle a PDF and be able to convert it into something usable directly. We did, however, find an online utility called Zamzar, which was able to convert the PDF to Excel, and then we had to go through a lot of manipulations to actually bring it into a usable format. Not only yield is tested in this, we also have measurements for the traits that you see here, and sometimes they provide environmental characteristics, whether it be the previous crop, so that you can have a function of what disease there might be, row spacing, the planting date, and soil texture, but that's limited primarily to the south from my experience. Once we go through all of this work, we end up with way too large of a file. We compiled 104,320 plot records for a total of 29 traits, including pedigrees. These pedigree records were compiled primarily from the uniform soybean tests, but we had to go into other sources to be able to fully connect the family tree that we were designing for soybean. So to do this, we looked at cultivar registration papers. JPR is a recent Journal of Plant Registration, is a recent journal that's taken this function out of crop science and other papers and put it in a central place. We also looked at Plant Variety Protection Act applications and patent applications to get some of the commercial checks that are included within this. And then other publications, so if there was a mapping population that was used for drought tolerance in Georgia, some of the lines that we're using directly in this or as parents for lines in this are in other publications. So we did an extensive search and managed to come up with a total of 36,500 records. Oddly enough, that's not rounding, that's the actual number that we ended on, which is rather convenient. We are looking at trying to get more granular data than this. Pedigree records are great, but if we can bring in marker data, that would be even better. That is an ongoing project that's being spearheaded by, I think, Dr. Aaron Lorenz, but currently that data has not been published. So moving forward, once we constructed the pedigree using the SynBreed package, we then constructed an A matrix, which shows the relationship between every one of the pairs of lines. This, since we had this 5,900 genotypes, we came up with a approximately 6,000 by 6,000 matrix, which we couldn't actually use in our modeling approach. So we reduced it using something called fuzzy C-means clustering, which works essentially similar to a PCA, where you can have multiple memberships and partial memberships within each grouping that it makes. Just an example of the pedigree. This is actually from something that I believe Dr. Michelle Graham did with her Shiny. It's manageable when you're only looking at, in this case, 5 generations, or 2 on either side, but we're looking at 43 generations overall, so there was not really a good way to visualize it. But the SynBreed package in R makes it much more manageable and is actually rather quick to generate this pedigree despite the scale of it. So into the modeling. For each one of the periods, we feed in a vector of the weather, the maturity group of the test, and then the clusterings that were generated to determine relatedness between lines. For the eighth period in the nth record, or for N1 through 104,000. It performs modeling for those traits for in this case, like the first week, and then it moves it on to model those and determines which variables are or are not important at that time point before moving the important ones to the next step, feeding in new information, modeling it again with those, and then determining at that point, are the old ones still relevant? Are the new ones relevant? And continuing to move on until we have a subset of only the ones that are only the variables that are actually predictive. And it goes into a linear dropout at the top and gives you the output yield prediction. The variables that we're using, we've seen the year is actually a rather good variable for this. It's able to correct some of the year-to-year variation and improvements in genetics over the years. The genotype is just the variety name. This is treated as a factor, so it doesn't try to say that genotype 1 is less good than genotype 2. The maturity group is invited also as a factor in this case, and then all of the weather parameters are entered as the normalized versions of those. And then output would be the yield, obviously. So getting into the results then. For the time points, we looked at how the record would perform whether we used monthly at the top, bi-weekly, weekly, or daily weather records. Although 15 time points, aka every 2 weeks, performed the best, we decided to go with weekly weather records, as we felt that this would better enable us to detect events like heavy rainfall. Instead of trying to average that out into a 14-day period, we're able to catch exactly when that's happening and model that with only a small decrease in the accuracy of the model. Going into this, I came up with a list of which variables I thought would be the most important for our yield predictions. I thought I did a really good job, but when we performed what's called a greedy search, so we take each variable, test whether it's what the RMSE is for only having it in the model, and then add the strongest variable, and then repeat the step, adding all of the remaining ones one at a time. We find out that the domain knowledge wasn't so good, even though this was based off of literature searches and things like that. So this was kind of interesting to me. It showed us that just because the literature says that something is important doesn't mean that it's necessarily the most important. But on the other hand, it may be that because some of these weather variables are interrelated in field environments, that one of these is giving its information that the other ones would normally give. So that's just kind of something that we weren't expecting, but we're going to be working on figuring out exactly when these are then important instead of just looking at overall importance throughout the growing season. Getting into the initial model performance, we wanted to look at initially we wanted to look at how it was going to perform within each location without including the genetic component. We got an R-squared of 0.7 or so, but you can notice if you look here, we have a straight line on the predicted versus observed. This is because it's predicting the same yield for every variety within that location, regardless of its genetics or what maturity group it's in or anything like this. So we thought we can do a little bit better, and it turns out we can. Once we add in the genetic component of this, our R-squared raises to almost 0.8, and we see that there's a much more granular prediction on this. On average, we can predict yields within 5.4 bushels in soybean. This is actually relatively decent, surprisingly enough. The LSD for most of these tests is around the same number, about 5 bushels per acre. So we're able to just distinguish the ones that would be able to be statistically differentiated within the test itself. We can likely improve this model by including other management factors, such as planting date, and also by including an improved relationship matrix, which would be possible with further marker data. We also tried predicting Iowa based on every non-Iowa state, and that did not go as well. We ended up with an error of about 10.3 bushels, but we thought, what happens if you just leave one location out? Turns out that leaving out a whole state, not a good way to go about it. Coming to an end, predictions, including genetics, management, and weather dynamics, will offer us as breeders a path to improve year-to-year performance in spite of the increased weather variability that we're predicted to be experiencing. These results also have potential for improved yield predictions without needing to do extensive physiological data collection like you would need to do with programs like AppSim, CropGrow, and other physiological modeling programs. And this approach can be modified for any trait in any crop and used within existing breeding programs as is. So you can take Pioneer or Corteva's breeding data, their historical weather data, and directly plug it into this model. And most likely they have a lot bigger of a training data set that they could use then and further increase the performance of this. As follow-up steps, we're looking to expand the training data set further. The period 2003 to 2015 that we used has a considerable portion of this with low climatic variability up until 2012. So we want to expand it both further ahead and further back so that we can get into periods where it had this increased climatic variability and hopefully be able to do better on predicting the extremes. We also want to integrate the markers that are soon going to become available, as well as any management practices that we have data for. I'd like to acknowledge primarily, initially, Saumik Sarkar, his grad students Triambik and Lin Jing, who have helped tremendously with the development of the LSTM model, as well as providing access to their GPU cluster so that we could actually process this, as well as Bhaskar's student Vikas Chawla for helping us access the weather API data, and then staff and students in the Sing lab as they helped tremendously with the data preparation. We'd also like to thank Iowa Soybean Association, USDA NIFA, the NSF P3 program, the Monsanto chair in soybean breeding, which is now somewhat taken over by Bayer, the ISU PIIR program, as well as ICIA. This time I'll open up for questions.
Questions for Jonathan? Great talk.
Thank you.
I really like what you come up with. So my question is, you seem to have a really large training set,
Mhm.
and how how big is it? Like how many environments you actually use?
So the question is how many environments are within this training data set? At the moment, we have 1,167 unique site year combinations. Some of these, though, they're testing maturity groups 1, 2, and 3, both uniform and prelim subsets, so you have a lot of different cohorts, if you will, of these varieties that are tested within there. But in total, a little over 1,000.
Have you tried to use fewer environments, and then how would that lead to your prediction?
So we haven't tried to use fewer environments except for the Iowa prediction. I'm not really certain. I'm sure that using fewer environments to train would lead to less accurate predictions just because you're not able to capture the patterns and the weather parameters at that point.
So do you think that at least 1,000 environments should be used to have this model?
I think it's a good start. I don't think there's a set minimum or maximum. I think the more you add, the more you're going to like your model. But you also have to start somewhere, and this took a lot of time to put this data set together. So,
Yeah, sure.
Aaron?
So, we have two related questions. The first is, what does the acronym LSTM stand for, and why did you pick that modeling strategy over others? And then related to that is, what is the technical reason, I suppose, that you couldn't use the full 6,000 by 6,000 pedigree matrix?
So LSTM stands for long short-term memory. It's a type of recurrent neural network that's designed specifically to handle temporal data. It's been used in sequencing and weather forecasting, actually, text prediction, things like this. So we used it because it was the machine learning model that was designed to handle the temporal data aspect. And, sorry, can you repeat the second?
What was it that kept you from using the full 6,000 by 6,000 pedigree matrix?
Okay, yeah, the thing that kept us from using the full pedigree matrix is when we're feeding in this vector, if you feed in something that would essentially push it to a 6,000 some long vector, and it would just, like, it's already taking about 7 days for a single model to run, and so that would like you increase the runtime on a, what's the, like sigma or 0 to the n squared with the size of the vector. So it exponentially increases the runtime as you try to add more and more variables. Sure.
So I'm curious about two things. One is how you test the predictiveness. What are you measuring against? And two, the fact that all the varieties that go into these trials already have proven performance.
Mm-hmm.
It's not like you're looking at a bunch of developmental material of unproven performance. And has this model been tested against developmental material in your lab?
So the way that we test the performance is we don't train on the full data set. We only train on 80,000 of the lines and then test on 2 subsets of 10,000 that it hasn't seen before. As to the second, and compare the prediction versus the observed yield reported. To the second point, these are to some extent developmental lines currently. They're F4 to F6 lines typically, except for the checks, which are then either commercial lines or things like Iowa 3023 that have been used extensively. So we do have some developmental. We don't have any way to, we could expand this to like F3 lines or something like this, but you don't have the granularity to predict within a single family differences in yield at this point because we're only going off of pedigree. So I hope that.
Could you at least predict the dogs and pick out a little bit?
Yeah, so that's one of the goals moving forward is we want to be able to predict based on these clusters, figure out what the optimum cluster value would be then So you can determine which parents are best going to fit that cluster for any given scenario of environments that you could come up with.
The ultimate question is, how big a yield difference do you need
Mm-hmm.
to get a meaningful prediction?
Yeah, and that's something that can only come with experience, I think. In soybean, if the LSD of these tests is typically 5 bushels in the uniform test as is, so we're coming up with something similar to that as far as the typical error. So I think we can safely eliminate, the bottom third of lines while still advancing the rest of it, reducing how much field work we have to do, but hopefully not getting rid of any of the truly outstanding lines.
Thank you.
So the current stage of the project, you're solely using weather plus pedigree, and it can achieve the prediction accuracy at almost 0.8.
Mm-hmm.
So by integrating the genomic data, the genomic marker data, how much do you expect to improve the prediction accuracy? And the second one is by using weather and pedigree data alone, you can already achieve 0.8 of prediction accuracy, and this is probably higher than solely using genetic markers. Do you have an explanation for why is that?
So I think I'll take the second question first. I think the reason why the weather and pedigree prediction is better than what pedigree or genetic markers alone can do is because we have so much weather dependency on yield specifically. In this, we're only testing yield performance. If you move to something instead like seed size, maybe there's not as much of a dependency on weather, so in that case, maybe genetic markers would be better. But I think with complex traits, you need to have definitely components of both the weather and the environment within your model to have any chance of getting accurate predictions. As far as what kind of improvements I think would happen with markers, I think if we can find a good way to model the genetic relationships, because again, we have to reduce it down to a size that the model can handle. So we have to choose only the SNPs that are actually predictive of interactions in this case. I think we could see a prediction accuracy of about 0.85, but that's just taking a shot in the dark really at this point.
Do you think that's the theoretical limitation of prediction accuracy in this model, or you can do higher than this?
I'm sure somebody can do better than this, but at this point, we don't have access to the markers, so we can't test it yet. And even so, we have some of the lines that are being tested that we don't have parentage records for. There's about 1 in 15 lines that we don't even have that part. So if we got access to that from either universities or breeding companies, then we'd improve some there. If we had the marker data, we'd expect further improvements. And then if you can determine exactly which time points, which variables should be important, if you include planting date so that you can better estimate what maturity stage it's at when it's hitting these environmental highs. All of these things I think are going to increase the prediction accuracy, but it's something that we currently just don't have access to that data.
On the flip side of that, all those are derived from how many donors to begin with.
Mm-hmm.
You have the markers for that donor set.
Yeah, but the thing is, a lot of the reason why we don't have parentage for a lot of this is because it's coming from commercial germplasm sources, even if it's being bred by a university. They have MTAs that don't allow them to share this, which kind of hampers us. But there's definitely been some work going on to work into tracing throughout generations these chromosome sections. You still?
At the beginning, show the equation like P equals mu plus G plus G, E plus G by E, right?
Mm-hmm.
And later on, when you produce a model, instead when you like put purely based on birth data, you get actually 0.77. Score is 0.77.
It was just 0.70.
70. Okay. Anyway, after you add like that pedigree information,
Mm-hmm.
the accuracy increase of 0.79.
Mm-hmm.
So I'm like, how do you like see this kind of like, I don't know what Yahoo you say both G and E are important,
Mhm.
but based on the prediction accuracy 10, it's like they, after adding pedigree information, only input a little bit for the accuracy, also like elaborate this kind of observation, I guess.
So as far as how we would break that down, one thing that we didn't try to do that perhaps we should have is just try running this model with the genetic component. I have a feeling with only 10 clusters that it wouldn't do very good. However, if you say that your weather has 0.7 r squared, you can't get the same from genetics, obviously, because if you get that on top of it, you've got 1.4 r squared, and I don't think that's possible. But it's definitely interesting to look at how each additional layer that you're able to add is able to improve your model. But you have to keep in mind that the prediction accuracy has to be balanced with the workload that it takes to generate that data. Thank you. Maria?
So related to that question, how do you think your very broad geographic range
Mhm.
here, seems from your map that you are evaluating materials over a big geographic range, which means a large variability of these environmental variables that you're using.
Exactly.
So don't you think that could be related to what he was asking you in terms of how the weather has such a significant impact on your prediction compared to the genetic?
Yeah.
So what would happen, or what do you think would happen if your geographic range is much smaller?
So we did try running the models instead with only the north or with only the south, based on which testing set that it's grown in. The north and south split zone is maturity group 4. They both grow maturity group 4, so there's overlap in environments. But when we did this, we had about a 40% decrease in accuracy. So we went from 5 bushels to 7 bushels error. But that does bring up an interesting point because Gisleis in 1994, out of Tommy Carter's lab, this paper looked at the relationship for soybean lines historically and found that there's, I think, 16 U.S. founders and a different set of, 16 northern U.S. founders and a different set of like 13 southern U.S. founders, and that these sets don't interact much except right along that boundary kind of. So you could definitely, with the founder thing, and going back into what Candy said, if you split it into north and south, then it's maybe easier to trace where each chromosome segment's coming from because you're working with a smaller set of parents. So yeah, I think if we had big enough of a data set, if we had 100,000 for just the south or for a subset, then I think we'd see better than we would for 100,000 for the full testing range.
Did you try taking out a weather layer at a time, taking out, say, rainfall, taking out solar radiation?
So on the greedy search, it's just the opposite of that. It's adding in one at a time. I don't know if that helps, but we did see, like, I removed it from this table, but the RMSC in this case is decreasing. It's kind of like when you add additional PCAs, the first one gets it down quite a bit, but then it's less and less improvement, and by the 4th or 5th, you're not making very much gain. Jumping?
So the breeding materials, they improve, genetically improve every year. So we expect the later year, the varieties will be higher yielding, right?
Mm-hmm.
So I think if you put just a time variable would be difficult to improve the accuracy. And another one is, how about just pick a single year data
Mm-hmm.
and use modifications just predict within one year data?
Mm-hmm. So for the first, in our models that we showed with the R squared of 0.7 and 0.8, we do have year as one of the input parameters in that vector that's going in. So we do have that, and the idea is that it's able to see early on is not going to be as good as later on. As long as you assume that it's purely genetics, there's still the weather variability, because across the board, you might have drought in, what was it, 2008? 12. Here's fly. But you have drought, and so when you would expect a genetic increase, you see because of the weather, you see a decrease in yield, so that doesn't hold strictly as a linear function. We did try training with 2003 to 2013 and predicting for 2014 and 15. We run into similar problems because 2014 and 2015 ended up having weather variables that were still extreme enough in one way or another that it wasn't able to do a great job. It got a prediction accuracy of about 0.73.